Hi, everyone. Dr. Stephen Linder here. We're going to be looking at the anatomy of the brain. These are going to be some models of the brain. So when we look on a bird's eye view, you see on the top left, it says we're looking at a superior view. We need to compare a gyrus to a sulcus, a gyrus to a sulcus. So when we look at the bird's eye view, the gyrus are what looks like the intestines, right? It's interesting because there's what we call the brain gut connection, where the brain and the intestines look much alike, and the intestines and what's in it has a major influence over the brain, right? What you eat can actually affect your thoughts and brain function. There's a direct connection there. So these are the gyrus. And then what we see, the valleys or the indentation, the valleys are referred to as a sulcus. Okay, gyrus versus sulcus. Now, when we look at the crystal skull here, and we look at the individual from the anterior perspective, and a little bit superior because we can see what's on top, the brain is divided into two cerebral hemispheres. This is the individual's left side. This is the individual's right side. So we have a right cerebral hemisphere and a left cerebral hemisphere. And we know that the two hemispheres are involved with different types of function. The left side, I kind of remember it with the L and L. The L in left with linear, with the L in the word linear. It's kind of like linear thinking. We say someone is really left-brained. This is someone that's really good in math, really good in science. The L again for language, the language center and the ability to speak is primarily on the left side of the brain. So left is more linear, language, math, science, whereas the right side is more your creative center, art, music, being able to match your clothes properly, looking at a room and being creative, saying, I think a couch would go good there. I think a shelving unit goes good there. I think the picture, we should put these colored drapes. That type of creativity is more right-brained, okay? When we look at a little bit of from a sagittal view of the brain, this outer portion of the brain is called a cortex or cerebral cortex. And the word cortex really means bark, not like a dog barking, but the bark of a tree, right? If you look at the tree, the outer portion, it kind of has these ripples in it. It has these gyri and it has these sulcus in it. So, anatomists said, hey, it kind of looks like the cortex. So we'll call it the cerebral cortex. And the cerebral cortex of the brain is gray matter. This is gray matter. And internal to that, we have white matter. White matter is myelinated, and gray matter is not myelinated. In the brain, the white matter is more internal. The gray matter is more superficial or external. But in the spinal cord, it does the exact opposite, meaning the white matter is more outward and the gray matter is more inward. So the spinal cord and the brain actually do a flip-flop when it comes to where is the gray matter and where is the white matter. And again, on a real brain, we could see that we have this cut. So you can see the inside portion is white. That's white matter, which means this is myelinated. And the outer portion, which is more superficial to it, this is all gray matter. That's the cerebral cortex. This is gray matter. It's unmyelinated. Now, when we look at the superior view, there is a fissure that's kind of in alignment with the bone that we would call where the parietal and frontal bone come together. Remember, there was a sagittal suture. So where the sagittal suture is on the bone, in alignment with that is a fissure called the longitudinal fissure. Longitudinal fissure, if you can get your fingers in between these, you can kind of pull and separate the left and right cerebral hemispheres from one another. You can't separate the brain. I've tried, I've done many brain dissections. What ends up happening is you can separate it a little bit, but it's still fully intact. There are quite a connection between the left and right hemispheres, lots of axons going back and forth. Okay, this, there's a few structures here. This is on like the internal lining of the skull, right? This is kind of like pulling off the cranium, and then you could see a few structures in here. This will come back again to, I don't want to say haunt you, but it'll come back again when you get into the circulatory system. You go over the heart, and then you go over the arteries and the veins. It'll be important to know these structures here: the superior sagittal sinus, the inferior sagittal sinus, the straight sinus, and then the transverse sinus. These are all ways of getting deoxygenated blood shunted away from the brain and trying to find its way back into the heart. Okay, so those are a few important structures. This translucent membrane right here that's kind of shiny, that's called the falx cerebri. The falx cerebri. Now we're looking at the brain from the posterior view. So this would be the occipital lobe of the brain. The green would be the occipital lobe, which is involved with vision, right? If someone slips and falls and hits the back of the head on concrete, they can actually go blind. Even if nothing happens to the eyes themselves, the eyes are only, they contain receptors. The eyes contain receptors that allow you to see information, but the actual seeing part is back here in the occipital lobe of the brain. So this is the occipital lobe. This is still part of your cerebrum. And then on the posterior and inferior part is another part of the brain called the cerebellum. Don't confuse cerebrum with cerebellum. They're not the same thing. Cerebrum makes up a big part of the brain that has these lobes, like the occipital lobe or the frontal lobe and the temporal lobe and the parietal lobe. That's all different parts of the cerebrum. The cerebellum is here on the posterior inferior portion. And between the cerebrum, or the occipital lobe of the cerebrum, and the cerebellum is another fissure running horizontally across in this direction. That's called a transverse fissure. So the falx cerebri was up here. This membrane here is called tentorum cerebelli. Tentorum cerebelli. It's going to separate the cerebrum from the cerebellum. Tentorum cerebelli. Okay, still a superior view. And you could see between the red gyri and this blue gyrus, there is an indentation here called a sulcus, but it's called a central sulcus. This is called the central sulcus. We can also see it from the lateral view. So what we're looking at is this structure. Now we're going to turn it sideways where we can still see the red strip and the blue strip. So here's the red strip and here's the blue strip. And between those two strips is this indentation called the central sulcus. And you can see it really starts where that sagittal suture is, or the longitudinal fissure, and it goes straight down the side, right? Straight down the side, right to the beginning of the temporal lobe. And the reason why it's called the central sulcus, it really is right down the center of the brain. We can see that. And this is anterior, and this back here is posterior. You can see a little bit of the green, which is the occipital lobe. So this would be the frontal lobe. Frontal lobe, occipital lobe, temporal lobe, frontal lobe, occipital lobe, temporal lobe. Okay, this red strip right here is part of the frontal lobe, and the blue strip here is part of the parietal lobe. The red strip is part of the frontal lobe of the cerebrum, and the blue strip is part of the parietal lobe of the cerebrum. The orange is part of the temporal lobe of the cerebrum. This red portion, let me see if it's coming up. Nope, not yet. This red portion is called the precentral gyrus. And if there's a pre-central gyrus, there's going to be a post-central gyrus. So we have a pre-central gyrus and we have a post-central gyrus. Between the pre-central and the post-central is the central sulcus. So hopefully it makes a little bit of sense as to how it got its name. There's a pre-central gyrus, there's a post-central gyrus, and then right in between is the central sulcus. Now, this is a really important part of the brain, the pre-central and post-central gyrus. Let me see if I can show you why that is. Let's do you know what, let's bring up homunculus. Let's see if I can bring this up on Google Images just to show you the significance of this homunculus. Okay, right here looks pretty good. Okay, so if we look here, you'll see that we have the two hemispheres of the brain, and there's a red strip and a blue strip, right? So now we see a red strip and a blue strip. The red strip is the precentral gyrus. The blue strip is the postcentral gyrus. So let's go here. The red strip is the precentral gyrus. The blue strip on both sides is the postcentral gyrus. Now, what information lies there? If you look at the picture, you see all different parts of the body. You see the lips, the face, the fingers, the legs, the tongue. We see the genitals. It's all represented by these two strips. Now, the blue strip for the postcentral gyrus, which is on the left, is sensory for all these parts of the body. Whereas the red strip on the right, you can see the red, is the motor cortex. So the frontal lobe, which is still red here, this controls the movement of all of these parts of the body. Whereas the blue strip, which is sensory, controls how you feel things in these parts of the body. And what's really interesting is that the parts of the body that require the most precision, like eye movement, lips, fingers, and hands, actually occupy more space, more geographical space of the brain than do the larger parts, like the thigh, the legs, the feet, right? So the larger parts don't look at the torso and trunk, don't take up much body, much space in the brain, I should say. But the hand and the eyes and the lips and the tongue take up a lot of space, whether it be movement for motor or whether it be the sensory part for the brain. So we call that the homunculus, but that's the pre and post central gyrus. So the pre-central gyrus on the left side of your brain will control movement on the right side of the body. And the pre-central gyrus on the right side of the brain will control movement on the left side of the body. Kind of does a flip-flop. So that's the importance of this pre-central and post-central gyrus, is that the pre-central initiates movement to all of those body parts, but on the opposite side of the body. And all of your sensation is going to end up here, coming up to the post-central gyrus. So when you have pain in the wrist or pain in the fingers, all of that is felt in the post-central gyrus. In order for you to move your body parts, the initiation of that starts here in the pre-central gyrus. Okay? So there's a little background information here. So here's your central sulcus, and then between the temporal lobe and the parietal lobe is this lateral sulcus, a lateral sulcus. Now, if we take the brain and we turn it upside down, we're looking at it underneath. This long cranial nerve right here is cranial nerve number 1, which is called the olfactory nerve. The olfactory nerve. Okay. Here, this is the optic nerve, which is cranial nerve number 2. Whenever we write cranial nerves, we always write them in Roman numeral. Where the two optic nerves crisscross, right here in the center, it's called the optic chiasm. That's where both of these crisscross. Okay, so olfactory nerve. I don't care if you differentiate olfactory bulb from olfactory tract. This, to me, is the olfactory nerve, which is sense of smell. And then this is the optic nerve for vision. This right here in the center, this is part of the brainstem. This is part of the brainstem. It runs right through the center of the brain. So this is the medulla. This is the pons. And up here is the midbrain. Those 3 sections make up the brainstem: the medulla, the pons, and the midbrain make up the brainstem. And I'll have another model that shows this in just a few minutes. So now we're looking at the cerebrum, and these are the main lobes of the cerebrum. Here is the frontal lobe. Here is the parietal lobe. Back here is the occipital lobe. And on the side is the temporal lobe. Now the parietal lobe, that's where your post-central gyrus is. That's for perception and sensory. And this is the frontal lobe, which is your motor strip. This creates movement. Up here, way up in the front, this is going to control your ambitions, your drive, most of your emotional state, your higher executive order of thinking. Your higher executive order thinking comes from the frontal lobe. When people lack ambition and drive, there's typically an imbalance here in the frontal lobe. When they have OCD behaviors, there's issues down here in this part of the frontal lobe. When people have body image disorders, there's problems here in the parietal lobe, imbalances here, where they may look at their body and say, wow, look at my left leg. It's bigger than my right leg. And I remember not too long ago, I had a patient that said that to me, Doc, look at the thickness of my left ankle compared to my right. And it looked the same to me. I didn't see any difference. But the patient swore that the left ankle was larger than the right ankle. So what did I do? I took a tape measure and I went around their left ankle, and I took the tape measure around the right ankle at the exact same location. And I had them read me the numbers. So it may have said like, 9 or 10 centimeters on the left, maybe 9 or 10 centimeters on the right. And they told me that the numbers were an exact match. So I said, what does that mean? And they were like hesitant, like confused. Well, they're both 10 centimeters going around. What does that mean to you? And they would say, it's the same. I go, exactly, they are the same. Then they would say, but look at it, right? So again, it was this battle between the imbalance and how they perceive things. People that have parietal lobe imbalances, these are people that tend to be clumsy on one side of the body. Maybe they're always knocking things over with their right hand, or they're always knocking things over, or have lack of awareness on the left side of the body. And I'll often, when I'm suspicious of this, I'll often have my patients draw a clock for me and write the numbers in. And sometimes I'll see them write 12, 1, 2, 3, 4, 5, 6. And then on the left half between 7, 8, 9, 10, there's nothing there, right? They don't have awareness of half the side. Just a little diagnostic trick there. Temporal lobe is more for hearing. Parietal lobe, we said, was perception, perceptual awareness. Frontal lobe was more for drive, ambition, goals, being really driven. So if people lack ambition or drive, and they don't have a lot of goals for their future, and they're just very sluggish in their approach to things, where they're never getting out of the house on time, they're always running late, frontal lobe imbalances. And these are all behaviors that can change as long as the brain is stimulated, or those parts of the brain can be stimulated properly. Occipital lobe is for vision. Cool. All right. So here now we have this a little bit more labeled. Here's the frontal lobe. Here's that red strip called the precentral gyrus. And remember, the precentral gyrus is the primary motor area, meaning this is where motor initiation takes place. And then just in front of it is the association area, meaning this works in conjunction with this to create movement. Okay. But thinking about moving takes place here, and then it relays it back to these other strips to create movement. Now here's the parietal lobe, and the blue strip is the post-central gyrus, which is your primary sensory area for perception. And just next to it, or adjacent to it, is the somatic sensory association area. Okay. On the posterior brain, this is the occipital lobe in green. Right here is the visual cortex. We said the occipital lobe is for vision. So the visual cortex is here, and just above it is the visual association area. So I'll give you an idea. You down the road, 5 years from now, you see me walking towards you. Now your eyes and the receptors of the eyes can visually see me, right? If your eyes work and the receptors work, then you'll see a person approaching you. Yes, I see that man. But it relays the information here to the visual association area for you to think, where do I know that man from? Who is he? He's so familiar. And then you'll be like, yes, he was the best anatomy and physiology instructor I ever had in my life, right? That's the visual association area, how it works. Okay, in the temporal lobe, this is where we have the hearing center. So the orange strip on top is the auditory cortex, and just below it, the association auditory area. And again, maybe the auditory cortex allows you to hear a song on the radio, and then the auditory association area goes, oh, I know that singer. I know who's singing it, right? It does all the interpretation of that information. Okay, we're going to skip this. We're going to skip the insula. Now we're looking at a sagittal view, meaning all we're doing is taking this part of the brain and we're going to rotate it, looking at it from the inside. So now we're looking at it from the inside. And we have a few important structures. One is the corpus callosum, which is right here. This is all white matter. And the corpus callosum is full of axons that connect the left hemisphere to the right hemisphere. It allows both brains to communicate with each other. This translucent area is called the septum pellucidum. The septum pellucidum is a very thin membrane that separates the lateral ventricles from one another. The lateral ventricles from one another. And I'll show you what the lateral ventricles are. They're basically chambers. They're a chamber that allows for the flow of CSF. And CSF is the abbreviation for cerebral spinal fluid. CSF, cerebral spinal fluid. And then down below, here is the fornix. And again, on a sagittal view, we have the corpus callosum. We have the septum pellucidum, this membrane here. Also in this, if you don't see the membrane is clear, you could also write lateral ventricle, and I'll show you what the lateral ventricles are. Actually, let me see if I can just fast forward it to that slide, and then I'll come back so it just makes a little bit more sense. Here. So here are the lateral ventricles. So this would be probably the best view, looking at it from a lateral view. This is all deep within the brain that houses cerebral spinal fluid. Okay, and the lateral ventricle, this is one lateral ventricle. And on the other side would be a paired other lateral ventricle. Okay, these are in both hemispheres. One lateral ventricle is on the left side, the other lateral ventricle is on the right side, right? But it's deep right in the center. So let me bring this back up now. So this will make a little bit more sense. So right here is that shape of where one of your lateral ventricles would be. And then here's the fornix, this other white strip. When we look at the underneath surface, you see these indentations. This is really the two cavities, the two indentations or cavities for each lateral ventricle. It's perfectly contoured for it to fit in both hemispheres. Okay. And then this membrane is part of the septum pellucidum, which separates the two ventricles from one another, the two lateral ventricles from one another. Still looking at the sagittal view, this was the corpus callosum. This was the fornix. There's the shiny layer called the septum pellucidum, which is where the lateral ventricle would be. And then here, this round structure is called the thalamus, whereas the yellow dot is called the interthalamic adhesion. The thalamus is the relay station for all sensory input. So all sensory information is going to find its way up the spinal cord, up the brain stem, right here into the thalamus. And the thalamus is a relay that knows exactly where to send the sensory information in the post-central gyrus. It'll know exactly where to send it, but it's the relay for all the sensory input, except for the sense of smell. The thalamus is the relay for all sensory input, except for the sense of smell. So this is the thalamus. Just below it is the hypothalamus. Remember, hypo means below. So this is the hypothalamus. Thalamus, hypothalamus. The hypothalamus is controlling the autonomic neural system. In lecture, you'll refer to it as the ANS. The ANS stands for Autonomic Neural System. The two main divisions of the autonomic neural system is what we call sympathetic and parasympathetic. Sympathetic is the fight or flight response. Fight or flight response, like you're running away from danger or you have to fight to defend yourself, fight or flight. What you're going to feel with that is like your heart racing, your breathing's going to increase, your pupils are going to dilate. That's a fight or flight response. The other part is the parasympathetic, which we call rest and digest, or feed and breed. Rest and digest, or feed and breed, that's the parasympathetic. So one's kind of like the accelerator and the other is like the brake. Okay. You're always in a driven state. You're always in a sympathetic state. But when the parasympathetics engage, then it kind of slows things down for the most part. The only exception is digestion, where the sympathetics don't speed up digestion, it actually slows it down. And when parasympathetics are engaged, it speeds up digestion, it doesn't slow it down. So it's the accelerator is the sympathetics, parasympathetics are the brake, except when it comes to digestion, it's the opposite. Don't worry about the mammillary body. Here, let's look at what we have labeled. Here would be the thalamus, and the brown would be the interthalamic adhesion. Below the thalamus, right here, this is the hypothalamus. And then we have the pituitary gland. The pituitary gland, remember, sits in the sella turcica, or the hypophyseal fossa of the skull. And the connection between the hypothalamus and the pituitary is what we call the infundibulum. It's like the stalk that connects the hypothalamus to the pituitary. When you get into anatomy and physiology 2, you will learn about the two divisions of the pituitary, the anterior and posterior division. And when you cover endocrinology, you'll go over the hormones that they release and their major impact on physiology. Okay, remember the corpus callosum, the septum pellucidum, the fornix, the thalamus, the hypothalamus, and right here is the choroid plexus. This vascular structure is the choroid plexus, and the choroid plexus is involved in producing cerebral spinal fluid, CSF, cerebral spinal fluid. On the posterior side, we have the pineal gland. Now, don't confuse pineal with pituitary. So here's the pituitary, here's the pineal, right? The pineal is pretty much adjacent to the cerebellum, Right here, this leaf-like structure is the cerebellum. That's the pineal. So the pineal or pineal gland that produces melatonin, and it's involved in helping you sleep at night. This portion right here, all of this is the brain stem. We have the medulla, we have the pons, and we have the midbrain. Those three parts, medulla, pons, and the midbrain make up the brain stem. That's the brain stem. Just a close-up view again. Here's the Corpus Callosum, Septum Pellucidum. You can see that shiny, clear, translucent layer. Here's the fornix. Here's the thalamus. That's the relay station for all your sensory input. There's the interthalamic adhesion. Below the thalamus, hypothalamus. There's your choroid plexus and the pineal gland or pineal gland. Okay, right here is the brainstem, and the brainstem is made up of those three parts that I just mentioned in the last slide: the medulla, the pons, and the midbrain. Medulla, pons, and midbrain. And I think right here is a good place to take a break. When I come back, I'll continue with the medulla, pons, and midbrain.